Okie dokie. So, this class, CS124, is a detailed, somebody mentioned on Facebook, you say introduction to in all of your classes, Caltech, and this is a very valid accusation, probably something we need to address. But it is a very detailed introduction, and I love it because by the end of this class, you'll be so familiar with so many different aspects of operating systems that you'll really have a very complete knowledge, and that's pretty neat. There is a hard prerequisite of CS24, particularly the last half of the course where we actually talk about operating system issues, operating system implementation details at a very high level, sort of the services that they offer and so forth. So that's why CS24 is a hard prereq. If you're an undergrad and you haven't taken CS24, you should be scared. I will probably make you drop it. I will probably force you to drop it. If you're a graduate student and haven't taken CS24, I'm a little bit more lenient because obviously you were probably an undergrad somewhere else. So you need to be clever and evaluate whether or not you have had equivalent experience. And this is a project class. This is one of those classes where if you haven't developed a certain level of coding maturity, Mike and I like to call it, then it will be a very challenging class for you because you have a ton of code to understand, and then you have a significant amount of code to write. And it probably is going to be more challenging code than most of the code that you've written so far. If that doesn't describe you, then good for you. You'll probably have a good time solving the fun and exciting and challenging labs. But it is very challenging because of the amount of code to digest and the amount of code that you have to create. So like I say here, the majority of the programming is in C. A small amount is in IA32 assembly. Approximately 10% of your class will probably be devoted to IA32 assembly because one of the assignments you'll have to write more than a little, but not a lot. And we'll use Git for version control. There are two things. One is that it will help you to work with your teammates, and the other thing is that it'll allow me to retrieve your submissions and then grade them. And obviously, if you're familiar with Make, great. If you're familiar with Doxygen, I have doxygenized basically all of the Pintos code so that you can generate documentation for it and follow links into the code. So there's some things I've been working on to try to improve the code base beyond what it sort of came to me as. And so if you're familiar with these tools, it'll definitely help. No exams, my favorite kind of class, because I hate exams as much as you probably do, maybe even more because I have to write them. And then I also have to solve them, so I have to actually know that the questions are good. And so the grade is taken entirely from the assignments. And about the last, I should say about 80% of the course is actually based on this instructional operating system called Pintos. There's probably 4 or 5 different instructional operating systems. And Pintos was developed at Stanford for their CS140 class. It's a very well-known class among people who like operating system classes. And it's used by quite a number of schools, actually. I'm not going to try to enumerate them because I don't remember offhand. But it's neat. It's x86, which all of you, if you've taken CS24, are familiar with IA32 assembly language. There's a number of them that are designed for MIPS. It's like, who here knows MIPS assembly language? Okay, so that's even less than I expected. There's usually 1 or 2 grad students who say, yeah, I had to do MIPS programming when I was in undergrad or something like that. So pretty straightforward. It's great. It's very simple. It basically has everything that is necessary and not much more. So it's a really good starting point. Now, I'm going to go ahead and give a little sales pitch, too. One of the things that I would like to do is if you really love this material, and besides wanting to be a CS24 TA, you just can't get enough, and you say, I'd love to do a personal project in operating systems. I would like to suggest you consider CS81 as an option, perhaps writing something on your own or writing something as part of a small team. One thing that is very interesting, there's a new language called Rust, which probably many of you are generally familiar with, and it's supposed to be good for systems programming. And I would love to see if somebody would like to, for example, try writing a microkernel architecture operating system in Rust. Perhaps that could be the next generation of our instructional operating system that we actually use for this class. So something to consider. Obviously, that's 10 weeks away. You may think you love operating systems now, and in 10 weeks, you're like, That's it. I'm going into show business. Or fast food, which whatever it might be. Anyway, all of this stuff is going to be on Moodle. Basically, assignments will be posted there. Slides will be posted there. Obviously, we're going to be recording everything so that you can go back and watch them, because they're very exciting lectures. I watch them all the time myself because I'm just so mesmerized by my own voice. But you can go ahead and sign up for the Moodle course. If you have your computer and your board, do it right now. The enrollment key is K-Thread, if I did that correctly, which is not similar to K-pop. It means something else. So, yeah, and basically I'm going to start using that for announcements pretty quickly. So probably by Tuesday or Wednesday, I'm going to start using Moodle to start announcing things. So just get signed up as quickly as you can so that I can actually let you know things. Now there's 2 books, which I already mentioned in email, so I'm not going to spend too much time on this, but they are completely optional. Books are so freaking expensive, it makes me really upset. Especially, I mean, I get them for free a lot of the time as a teacher, but it still frustrates me because you're it feels like taking advantage of people when you have students who don't have an income and you're like, okay, yeah, you only have to pay like $930 for this book. So, I generally try to make sure that they're optional for my courses. So Operating System Concepts is a really good book. We follow loosely a lot of the material in this book, and you can see that one of the authors is actually the same as the Database System Concepts book, so Silberschatz is the same. He worked on both books. But it's very high level, and one of the things you notice is that most of the time the devil is in the details. So high-level coverage is nice, it exposes you to the concepts, but it doesn't show you all the real nitty-gritty details you have to get into. Then there's Understanding the Linux Kernel, which is like my favorite book of all time when it comes to understanding operating systems, because it actually goes through all of the details of how Linux works, and it probably covers the vast majority of the kernel source code and explains how all the different mechanisms work. And it's a very detailed book. You know, even me, I've been programming for nearly 30 years now. Is that right? Yeah, it's been a long time. And I have to read sections in this book multiple times just to make sure that I actually understand all the details of what's going on. But it's a very, very deep book, very valuable. And since Pintos follows Linux architecture pretty closely, not super closely, but closely enough that there's a strong similarity, I think that it is very helpful to have a copy of that book available somehow. Okay, so like I say, your teams might want to get access to the book. I will try to give you reading pointers to the second book because it's really nice and helpful, but there's no assigned reading. If you decide you don't want to get these textbooks, that's perfectly fine. I think you'll be able to do the class perfectly well. Okay? See, assignments. So there's 6 assignments, and we're going to start with the first assignment on Wednesday or Thursday at the latest. It'll go out. Write a basic operating system shell. It's kind of a hey, this is systems programming type assignment. It seems challenging until you get to the later ones. Second one, write a bootloader, and then you have the Pintos assignments. You do kernel level threading, thread scheduling, system calls, so you get to start understanding the separation between kernel mode and kernel space and user space, and the various details around that. Virtual memory system, which is kind of scary because they say implement virtual memory for Pintos in this directory, and you go into the directory and it's empty. You're like, oh man, this is gonna be a long 2 weeks. So, and then the last thing to do is to extend the file system. Pintos comes with a file system, but it's fixed extent and it's continuous extent file system. So files can't grow and they can't be sort of spread across the disk in multiple sections. And so you'll implement something like Linux's ext2 file system format. Okay, so that's basically the lay of the land. What you'll notice, if you do the math, and it's complicated math, is that the assignments end up spilling into finals week. So I guess you can sort of consider the file system to be your operating system class final. Yay. But anyway, it's pretty straightforward stuff. I don't think that it's going to be too terrible. And obviously the 2-week assignments will be worth more than the 1-week assignments. All right, so that's straightforward. The assignments are hard, and I was already I don't want to oversell this because sometimes when you tell students this stuff is really hard, they carry that into their minds and they're like, I'm going to have a real difficult time doing this. Honestly, operating systems are glorified bookkeepers. That literally is all they do. The part that makes them challenging is that everything happens all at once at the same time. That's the part that makes it challenging. But it is just a big glorified bookkeeper. So it's not like conceptually it's hard to understand. There's parts of it that are. It's just that there's a lot of things going on and you have to think it through. And so that's the part that makes it hard. I don't want you to get scared off of it. So what I do is I require you to work in groups of 2 to 3 students. And it's not that people can't do it by themselves. People have done it by themselves. But the number one issue, do I mention this? Yeah, is that you'll have somebody to talk to about debugging, which is so helpful. I was really astonished at how big of a difference it made to have other people to talk to through bugs. Because a lot of times it is, blah, 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 I have this issue, and then, oh, that's the problem. And you realize and you go, and in fact, I think there's a technique called, what is it, like rubber duck debugging, where you have a rubber duck on your desk and you describe the problem to the rubber duck and then you realize what the problem is. So, and that way you don't bore another human being. But, you know, it's nice to have somebody else to talk to about this stuff. So, of course, we encourage you to think very carefully about whether you are going to commit yourself to the entire course, because if you decide to drop it, will affect other people. I'm going to try to manage this as actively as I can this term. So, you know, I don't want anybody to think I have to, like, not drop this course, you know, even though I've got, like, an F minus 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 and, you know, I'm already on verge of getting UAShed or whatever. You know, that's, we'll figure something out, okay? You should drop a class if it's really bad for you. But I do want you to think about this ahead of time more because it does affect other people. Okay, yeah, and we will be able to adjust teams if necessary. Okay, so I mentioned Git. I'll create those repositories on the CS cluster. And I don't care if you work in another Git repository. You know, a number of people seem to like working on various public Git, you know, hosted Git systems, which is neat. You know, it's neat because you have things like bug tracking or other things that are provided by those systems. I just need to make sure that your code makes it into the repository that I create so that I can actually, you know, so I can actually grade it. Now, I say here I give you the code base for the course as part of the first assignment. That is probably an overstatement. What I will do is I will give you some portions of the code base, and then I will give you the bulk of the code when the third assignment rolls around, because that's the first real Pintos assignment. I don't want you getting bogged down, distracted with other things, so I'll probably start with something small, and then we'll grow it from there. So, but once you set up a Git remote, you can just pull from it anytime, and it'll all be cool, so you won't have to worry about that. Okay, so honor code, collab policy now operates at the level of teams, not at the level of individuals. So teams must create their own submissions. They can't share implementation code, but you are strongly encouraged to share other things like ideas and debugging help. And wow, I tried this and my computer exploded, so don't try that yourself. Okay, things like that would be incredibly helpful. In fact, I typically set up a piazza to help with this class where people can go and post questions and so forth, and then other people who have figured it out can help. I might actually do some kind of point bonus for that kind of thing so that we can encourage collaboration more. So I'll have to sit and think that through. Anytime you create an economy, you have to make sure it can't be gamed very easily, so you have to think about that stuff. Also, Pintos has been around for, what, 10 years now, so please don't go look for solutions online. I would really like you to not do that. I think that's all I'll say about that. I think it's just obvious. But the other thing is that if you decide to go, like, jump into the Linux kernel or Linux operating system implementation, I'd be happy for you to do that. I look at that stuff frequently when I'm trying to figure things out. And it's like a really good idea to go look at some sophisticated working implementation to get ideas. So don't copy code. You need to understand it. And I have in the design documents a section where you cite external sources. Because if it's a really good external source, then I'm going to share it with everybody in the class. I want to make sure that that kind of information is shared. So, but don't copy code. If I discover that you're copying code, then it's going to be, I'm probably going to be in my office crying. and then we'll have to follow whatever process there. So anyway, just make sure that you understand what you do and create everything yourself. Assignments and due dates. So Thursdays at 2 a.m. I don't know why. It's just what I've settled on. So that's what we'll end up doing. Late penalties are typical for my classes. So 1 day late is 10%. I don't care if you're a day late too much. 2 days late, and if it's like 1 day late and you're answering a ton of questions on Piazza and I figure all that kind of stuff out, then it probably will all wash out to be exactly the same. 2 days late, it's compounding. That's probably the wrong use of compounding, but 3 days late and so forth. You can see that after 4 days, it is too late. Teams have late tokens. This is always an interesting situation. Teams have late tokens, so you have up to 4 that you can use. No questions asked. And of course, students can also request extensions in various other ways. So, look, Donnie, I'm deathly ill. The health center said I almost died 4 times in the last 6 weeks. Can I have an extension? Sure, if the health center said. Dean's office, sometimes those are a lot more serious situations that might arise, but we're perfectly happy to accommodate those things. It's a challenging thing to figure out. One student in a team decided, I shouldn't say decided, they decided to get sick. One student in a team got sick, and obviously that affects the whole team. So I need to figure out exactly how to grant extensions in that situation. That's an area that is unclear to me at present, but we'll iron those situations out. Okay? Let me see, is there anything else? Okay, let me just ask, are there any logistical questions right now? Because I think that's the bulk of the logistics for the class at this point. Anybody? Yeah. How are teams getting made? Through a complex process that is a mystery even to me at the moment. But no, the idea is that everybody has this survey that I sent out. I want you to fill it out and say, these are people that I would like to work with. And then what I will do is write a program to solve the matching problem of trying to figure out who should be paired with who. So obviously, if you say this is the team that I would like to work with, then that is probably going to be your top priority as far as who you actually get to work with. So what I'm hoping is that I will get to tweak things and I won't have to generate things from scratch. But there's always people in these classes who don't know very many people and they don't know who to work with. And so I want to try to use the other questions in the survey to try to place people properly. So that's the idea. And I have no idea if it's going to work well, because this is an experiment, as I told you. Okay? So if you have any ideas or concerns about that, please share them with me in email, and I will be happy to take that into account. Yes? I'm going to try to make sure you know your teams by Wednesday. So obviously that means I need people to fill in their surveys as soon as possible. I've gotten probably 12 and a half, so I need more. Yes? That is correct. Yes, you can email it back. I would love to have an actual online survey or have you send me properly formatted JSON data, but I thought both of those were probably too much difficulty, so I said just send me back the text file. Yeah. Any other questions? All right. Thank you for being my guinea pigs, and I hope it isn't something you regret. All right. So Pintos is designed and implemented to be built and run and exercised on Linux. It all runs in an emulator, so it's not like you have to have a special machine for it. The very first time we offered this class, 2 students sat down and actually figured out how to get it to run on OS X, and I was quite amazed, and they sent me the instructions, and I said, no one will ever do this, so I burned them. So, but there's a lot of interesting nuances. Processor emulators are actually surprisingly dependent on their host platform because they do rely on emulated services provided by the host platform, and so that can definitely have an effect on how they behave. And so I want you to have something that is as uniform as possible. And so I'm going to be testing on 32-bit Mint Linux, which is what I've been developing with for this class, and it's what I will give you a virtual machine with this Linux. If you hate Mint, I'm sorry. You can figure out how to set up your own 32-bit Linux platform. It is super simple. I just picked Mint because I wanted something simple and not horrendously heavyweight. So that's why I picked that. But yeah, if you want to do some other Linux platform that's your favorite, that's fine. It just should be 32-bit. Okay. So yeah, I'm getting the virtual machine set up for you right now. There will probably be various little details that need to be ironed out through the progression of the course, but I'll just send emails to the class when those things need to be done. But I'm getting it set up with all the tools I think you will need right now, and probably even a few more. For example, a number of people, who here is familiar or has heard of Bison and Flex, aka Lex and Yak? Okay, so command shells are pretty straightforward except for one annoying thing: parsing the freaking command line. So a lot of people hand write that, and there tend to be a number of bugs in those areas. Some people write them with a Lex and Yak equivalent. So you're certainly welcome to do that if you wish. So that is an example of a tool that's on there, and I think it's only needed for assignment 1. Okay. The Pintos testing code relies heavily on Perl. I hope that is the only way we'll ever need Perl in this term, is to run the test suite. So things like that. Okay, any questions? All right, that should also be available by Wednesday. Interestingly enough, you can write a command shell entirely on whatever Linux or even on Windows platform you would like, but then you notice that there's certain system calls that are slightly different on different platforms. There's various other things that vary from platform to platform. So I want you to at least test your submission on Mint Linux or on some other 32-bit Linux platform, because I definitely know that Linux and OS X vary in what they offer. So keep those kinds of things in mind. I mean, this is the world of systems programming. Welcome. It sucks, okay? What else can I say? Also, last detail before we dive into some other sort of background material is that you'll notice that all the way through we basically spend most of our time talking about how Unixes do it, or Unixen they sometimes say. So primarily Linux, but I don't want you to think that this is some kind of, oh yeah, and I wanted to also, this is a terminology point, that when we say Unix, I don't mean SCO Unix, SCO being the most annoying company ever, but there's a whole family of Unix-like operating systems, and OS X definitely falls into that category because OS X is actually based on a microkernel architecture that was developed at CMU, if I remember correctly. We'll talk about that in the future. But this is the thing I wanted to say. These concepts appear in virtually all operating systems. And Unix is just, or I should say Linux and these kinds of operating systems are just the easiest to experiment with because they were kind of designed to do that. And they were, they're made widely available, so it's easy to get something to experiment with. As an example, I mean, there's things that Windows sucks at. When I talk about the Windows process scheduler, it's like, why did you do it this way? But then there's other things, like Windows has a really innovative threading implementation now, like starting in Windows 7, I believe it was, or in Windows 8. I can't remember offhand. But Windows does something that is completely innovative that you don't see in virtually all other operating systems. So when we get there, I'll talk about that. They all have strengths and weaknesses. Okay? So it's a great place to leave ideology behind and just sort of focus on, well, what are actually good and bad aspects of all of these systems. So I don't want to be somebody who's a fanboy, unless there's real reason to. Okay, what is an operating system? How would you describe what an operating system is? Large, complex. I like sophisticated bookkeeper, but there's a purpose behind it, so that's not a very good explanation. Yeah? It controls access to the system's resources. That's a really good answer. That's about half of what an operating system does. It controls access to the system's resources. What else? Any other ideas? Okay, well, that was a really cool answer. So, did you have an answer? Or idea? Yeah, I like that one as well. It exposes the system's resources to the end users. Those 2 points actually capture 99% of what operating systems fundamentally are responsible for doing. Great answers, guys. Most generally, operating system provides applications with a standardized interface to the computer's hardware resources. We'll talk about why you need a standardized interface, but you can probably already, if you've taken 5X, you know. But, it's just the reality that there's all kinds of disparate pieces of hardware involved. The other part, the operating system manages the allocation and sharing of hardware resources to applications that want to use them. So this is sort of the governing side of things, that the operating system has to control who's allowed to access what and when. And there's tons of variations under this theme. So we're going to spend a little bit of time at the beginning of the class exploring these topics. What kinds of devices the OS runs, how the OS is architected. I mentioned microkernels. That is a particular architectural pattern in operating system implementation. And what other facilities, services, and guarantees the operating system provides. File systems are a great example of this, because we have all these different kinds of storage media that you can plug into a computer. What are some examples? I've got like my USB spinning magnetic rust bucket that I plug into my laptop every 10 days when it nags me about having not backed it up recently, and so I plug it in. So that's an example of a storage device. What are some others? Yeah? NAS, network attached storage. So that's a really interesting one because I actually access storage through the network. What are some other ones? There's tons. How about just connected directly to the computer? Yeah, flash storage. So you have a couple of different kinds of that. You have solid state drives. You have little memory cards, SD cards. Like I have a little SD slot on my laptop. You have USB flash drives as well. Something else, something spinning. Optical discs. I mean, how many people have computers without optical discs now? Yeah, it's becoming more and more. I like get a CD and I'm like, oh wait, where do I put this? Okay, I guess the microwave is it. So, you know, but you have all these different kinds of devices that you can have plugged into your computer. And of course, we haven't mentioned internal hard disks, RAID arrays, which are frequently exposed as single storage devices as well. So, and this is just hard disks that I have on this slide. So parallel ATA. Does anybody have an IDE drive that they're actually using right now? Yeah, because I have a box of old drives too. But okay, so nobody has a computer with an IDE drive right now that's actually using it. Serial ATA. There's what is it? SAS now, serial attached storage, which I didn't include here. SCSI, which is becoming less common. SCSI is becoming less common, but that used to be really common for server systems. When I was a wee lad. USB drives that can be plugged in and unplugged. And of course, you have different things. You have sizes, and then you also have how old the device is, because we're starting to see variations in devices based on their age. So you had earlier disks that would use this rinky-dink mechanism, which was really great at the time, cylinder head sector addressing. This is what I grew up with, cylinder head sector addressing. It imposes this limit on how large a disk can actually be. We're going to spend some time talking about that in the future. But you also have this other issue that cylinder head sector doesn't actually reflect the disk layout anymore, because now, you know, I have these zones on the outside of my platter which have more sectors than the zones on the inside, because I can fit more space. I have more space to fit data in close to the edge of the disk. So later disks introduced this thing like, okay, just give me a number, and then I'll give you the block that corresponds to that number. So that's logical block addressing, which can go much, much larger. You know, they made the value that it takes much larger so that you can just access blocks very easily. And now the disk is responsible for doing that translation. But the OS has to figure out, okay, what do you need? And it talks to the drive and figures out what it needs to use to interact with it. You have different kinds of maintenance. I don't know if you think about that very often, except when your mom or your grandma calls us, my computer's slow, and you're like, okay, well, did you defragment the hard disk and all of that kind of stuff? Well, that's maintenance that the operating system has to deal with. And different kinds of storage actually require different kinds of maintenance. So magnetic disks, why are they sensitive to fragmentation? Yeah, because slewing a giant disk arm over the surface of the platter is slow. It takes milliseconds. And every computer that I know of gets really bored when milliseconds of time go by before it can get data. Okay. So that's slow, so we need to worry about fragmentation issues. Solid state drives, they don't care about fragmentation. But they have other issues. Anybody know what the issues are? Yes? Okay.
There's one, I forgot which one it is, but there's one combination of them that causes it to slow down by, I think, like at least 2x.
Okay, so writes, repeated writes, and then reads after writes. Those are good examples. These don't fundamentally get to the way that the solid-state drive works internally, which we have some lectures talking about it. So if you don't know, don't worry. We'll talk about it. Yeah?
You can read from a smaller section from then the amount you can write. You can only write to a whole block at a time. You can read from a smaller.
You're on the right track. You're really close. You're really close. The issue is that you can actually read and write to the same size blocks on a solid-state drive, but erasing is on a really large block. Once the block is empty, then you can write to it. But you can only erase really large chunks of memory in the solid-state drive. That's the issue here. So basically, we have a couple of different things that we need to think about. We have to erase blocks before they can be written to. So I write to it. I can't, it's very different conceptually than a hard disk, where I can just plot different data on top of the old data in the sector. In a solid-state drive, I've got to actually clear that thing, and then I can write something new to it. Okay, so there's an interesting issue there. And like I say, blocks can only be erased so many times before they wear out. So the operating system needs to interact with the solid-state drive in a very careful way to avoid causing issues. They also might have different file system formats. So there's a file system format, ISO 9660, which basically all optical drives use. And then you have the hard disk, and then you have the pluggable little flash drives, which are a different format. Most of them are FAT32, unless it's larger than 4 gigs, and then you have to use something else. So it's pretty common now. And then Windows and Macs have different file system formats and so forth. So there's all these things. So this is how Unix interacts with files. Open, close, read, write. And it doesn't care, I should say the application doesn't have to care what kind of device it is, because the operating system provides this unified interaction mechanism for interacting with the computer. And there's a virtual file system where all of the things, no matter what kind of drive they're on or what specific drive they're on, they're all exposed in this unified layout that you can access very easily. Okay. I'm going to pick up the pace because we're getting a little bit behind. I get too excited about this stuff. Okay, now, let's say you want to open a socket. Or you want to open some other kind of like a pipe to another process or something like that. Well, it turns out that the interface is exactly the same. Open, close, read, write. Well, open is the part that changes. But close, read, and write are all the same. Seek, if the device supports seeking, then that's available as well. The only real difference is how you open the device. And we'll talk about how these things are provided next lecture. But you can see how the operating system provides this unified abstraction to all of these disparate kinds of hardware. All right, does that make sense? Okie dokie. Now here's another one. Multiple processes can manipulate the same file. So here's a scenario. Process A opens foo.txt to read and write it, and then B comes along and decides it wants to delete foo.txt while A is still running. So what should happen? Different operating systems have different answers to this question. A lot of times Windows will just say, no, you're not allowed to delete this file. Does anybody know what Unix does? Yeah.
Isn't it just leave it, we kind of leave a weird ghost thing running until the last process looking at it dies?
You're very close to the right answer, yes. Yes. You're talking about an implementation detail that's actually not relevant to the conceptual, what is the model that it provides? Yeah. So the answer is, I'll just go ahead and give it to you really quickly, is that B is allowed to delete the file, and what happens is the directory entry is removed. The file data exists somewhere else on the platter, or on whatever device it is, and the operating system keeps a reference count to that data. And when that reference count hits 0, the data is reclaimed. So what happens is B deletes foo.txt, removes that directory entry, so nobody else is allowed to open it anymore, but A is still using it, so the OS leaves the data in place until A terminates. At the point that A terminates, the reference count of that data hits 0, the space is reclaimed. That's how Unix solves that problem. Is that the only right way to do it? No. It's just the way that Unix picked to do it. Okay? But you can see here that when you have hardware resources shared by multiple processes, the OS has to figure out how to solve these kinds of problems. It's the arbiter. That's why I really like, there's a description in the operating system concepts book of what an operating system is, and it says an OS is like a government for your computer. It doesn't have any inherent purpose to exist beyond giving programs an environment in which they can get work done. That's the same way a government is. Okay? I can't break into my neighbor's house and take his TV because the government will come and say, you're not allowed to do that, Donnie. So now my neighbor's allowed to live next to me without worrying when I eye his TV. So, same idea. So in UNIX, so we already talked about this. Let's go back a little bit and look at the history of operating systems, because this will tell you basically why things are the way that they are. I find it really interesting. Basically, early computers were mainframes, and so you would have some kind of job that you wanted to perform, and it would be a stack of punch cards that you use to feed into the computer. And so you can see what the job actually contains. You start off, I want to run a Fortran program to process data. So the first part of that job was actually the Fortran compiler. And that gets loaded into the mainframe. And then you have the program, which goes into the compiler, and the compiler generates the machine code into the computer's memory, and then the data goes into the memory, your program processes it, and then the output goes somewhere. So that was all done by a human operator. So the mainframe does its thing, and then the results are printed out on one of these old, like, or a daisy wheel printer. But basically, those really cool stacks of, like, accordion fold paper with, like, the little punchy holes on the sides. I don't know if any of you have seen that. I'm going to start getting to the point where I'm talking about technologies that no one has ever heard of in my classes, which will probably make me cry. But you can see that you're spending a lot of time waiting in the system. And we're talking about a very expensive computer. I'm waiting for the operator to put the cards in. I'm waiting for the cards to be read. I can't really do any computing. I'm waiting for the program to read its data. And then at the end, I'm waiting for the printer to print out the results. So the CPU is actually sitting idle quite a bit. So this is kind of what people did, is they said, how can I solve this problem of the thing being slow? And so they said, well, let's batch up jobs instead of just having a single job. So you'd have a simple computer that didn't cost very much, and the operator would sit and feed it cards, and it would write the data onto a tape. That looks very much like that one. Obviously, that's, well, actually on the slide it's about to scale. It's quite a large tape. And then the mainframe takes the tape, and it just reads the jobs in sequence and executes them. And then the results go to an output tape. So now you've improved the speed of the I/O. You don't have the operator sitting there getting in the way of the mainframe anymore, so that's faster. And you could also have certain tapes that were always present to have things like the Fortran compiler that everybody used. Okay? And then the output is, the tape is taken somewhere else and the output is printed. So this helps improve the speed that things could get done. But then they realized, well, there's another problem, because if one job is waiting to read data off of a tape, and it's got tapes are great for sequential access, but they're horrible for random access. That's why we like disks so much, because they're much better at random access than tapes are. And so, the computer is basically sitting there waiting to seek until it can perform an I/O. And then complete the I/O takes time as well. So, what this introduced was this notion that, well, while one job is waiting to perform a task, let's switch to another job. So that's multi-programming. So, like I say, if the mainframe can keep multiple programs in memory, then I can actually get things done faster. You can see how all of this is like, how can I maximize my investment in this expensive large machine? How can I get things done faster? This was sort of the motivation all the way through. Okay, we're still in a world where a university would have one of these. So, or a company would have one of these. Now, what if you have multiple jobs running at the same time? Now you need to start sharing your computer's memory across multiple programs. These programs are not necessarily written all by the same person or team or company. And so basically you had to have some way of separating out each program's data and making sure that one program couldn't access another program's data. Okay, so this is the memory in the mainframe. And so we have to start providing process isolation. If we're going to have multiple things happening at the same time, and we don't trust them all to get along, then we need to be able to isolate them. So you can start thinking, okay, I remember CS124, process isolation, virtual memory. I have to have some kind of virtual memory abstraction. And then you also have to have some kind of operating mode differences in the way the CPU is implemented so that one process can't just change the mapping back to something else. The OS can have more capabilities and the jobs can have reduced capabilities that will keep them from causing trouble. Okay, does that make sense? So you see how this develops over time. Okay, the other issue. I carry my punch cards all the way across campus and hopefully I don't trip and the punch cards go everywhere. There was an interesting thing, if you have a shoebox full of punch cards, what people would do is they would draw a line across the side of them, like at an angle or something, and that way, you drop all your punch cards, you pick them all up, you put them into the box, and you're like, oh, the line doesn't go like it used to, and so you can reorder them and put them into the right order so that you can do that. Obviously, if you draw a perfectly parallel line, you're going to be sad. It's not going to help you at all. But anyway, you take your punch cards, you give them to the operator, you go and, I don't know, play racquetball for 6 hours, and then you come back and they say, okay, here's the output of your program. Syntax error. Great. So you see that debugging was very different in this world. You studied your program like crazy before you even took it over to run it because you had such a long turnaround to find out if something was wrong. So time-sharing systems basically allowed you to have a little terminal that was connected over network to the mainframe. The terminal was dumb. It was basically a keyboard and monitor. And it would connect to the computer, and you could type and do things. Okay, so you can see that this is an extension of multi-programming, and that instead of just having multiple programs, now I have multiple users. So this is where multitasking becomes a thing. I have process scheduling to consider, all of these kinds of things. I want to maintain interactivity, but I also want to be able to have compute-intensive processes run well. Okay. And it's interesting because the mainframe is still expensive, and if you had only one user, then you're wasting a ton of money because the user is the slowest thing that the computer's interacting with. But if I have a bunch of users all talking to the same mainframe, then I'm going to keep that CPU pretty well utilized. And there were all kinds of billing systems designed with that. I mean, there was just a ton of different mechanisms. Studying that part of computer history is actually really fascinating. I could point you at some books if you're curious about it. Okay, so you have integrated circuits. Computers get cheaper. Suddenly it's not tens of thousands or hundreds of thousands of dollars to buy a computer, so the whole company shares one or the whole school shares one. So now we start giving departments computers. So these are mini computers. If you hear that term, it doesn't mean like your watch or your laptop or your phone. It's a computer that's actually shared by a department or a group within a company. And then, obviously, this process continued, so you now have microcomputers where basically, it's interesting because now you actually have people interacting with the computer who don't care so much about how it works or how to program it, or things like that. Now you have people who want to start doing things without actually understanding all the nuances of the machine. So this is where graphical user interfaces really started to catch on. They became necessary because mom and grandma don't want to learn C so that they can write their program to compute their recipes. They want to just use Excel or something like that. Now, graphical user interfaces. Does anybody know when graphical user interfaces really started becoming a thing? I love this stuff. So, none of us existed in 1960s. That's my guess. I think I'm right, yeah. I'm probably the oldest of all of us, and I didn't exist in 1960s. So, there's this guy, Doug Engelbart, who, if you look on YouTube, you'll see this thing, the mother of all demos. And he demonstrates a graphical user interface that he created. It has a mouse. It has a graphical drawing program. It has a collaborative hypertext, collaboratively edited hypertext system. You think that Google Documents is like amazing in the wave of the future. Back in the 60s, seriously. You have streaming video conferencing. All of that, he and his team came up with all of these ideas. So they've been around forever. And that's one of the things I love about operating systems is it gives you a sense of history. You know, I think, oh, I'm implementing this cutting edge thing. Well, actually, it probably was invented in the 60s, okay, or the 70s. Okay, so processors continue to become less expensive. So now we can have multiple processors in a computer. Remember, if you remember your last half of CS124, physics becomes an issue. We can't make them go faster and faster and faster. So we start adding more of them. So you have multi-processor systems. And the processors are in different packages. So now they have wires they have to communicate across, you know, out of one device and into another device. And then you have multi-core systems which put multiple processors in a single package. There's companies now where you can get, for not too expensive, 64 processors in a single chip, and you can program it to do stuff. And of course, I would say GPUs are another approach to the same thing, where instead of having like 64, 128 processors, you have a few, but they're very streamlined, very good at executing in parallel. And of course, having a multi-processor system requires OS support, because now the OS literally has multiple things happening at the same time. If you have a single core system, there's always only one thing happening, even though it looks like there's a bunch of different things going on at the same time. Once you have multiple processors, it becomes a lot more challenging. You should be thankful that Pintos is a single processor operating system. I wish I could have you work on a multi-processor operating system because it's so exciting, but then no one would probably ever complete the class. So anyway, of course you can continue this process. Well, now we can actually emulate. Processors are powerful enough to emulate processors on processors. It's crazy. So now we can actually run operating systems hosted in another operating system. So you can see that you have a host and a guest. You have two different approaches that you frequently see. You have emulation, which is where one CPU emulates a different kind of CPU. Anybody here been a Mac user for like ever? Like really long time? Do you remember Rosetta?
Yeah.
Rosetta was really cool because you have PowerPC programs that were written for OS X and blah, blah, blah earlier on, and you need to be able to run them on the new Intel Mac. How do you do that? Well, the instruction sets are completely different. So Apple provided a program called Rosetta, which would emulate a PowerPC on an Intel processor. And that would allow you to keep using all of your programs. It would be slower, but it would work. I thought that was so cool. And then you have virtualization, where basically you have the host and the guest actually run on the same kind of processor. So now the processor can actually provide hardware virtualization support directly to the guest to make it even faster. So now that everybody's basically a peer, although you have sort of a junior peer and a senior peer, running on the processor. Okay. If the processor is not capable of doing hardware virtualization, then you have to start relying on emulation again, which many virtualization environments actually are able to provide. So VirtualBox will probably be your friend or your mortal enemy by the end of the term. So that's an example of an emulator. It can certainly rely on hardware virtualization if you have it available. And it's becoming more and more common. So you're seeing this supported in hardware more and more. Now, you have that thing that sits and manages the guest operating system. We now call that a hypervisor as opposed to a supervisor. And it has mostly the same concerns that a regular operating system does. I mean, it's funny because it's kind of an OS for operating systems. It enforces isolation between guests. It manages access to hardware resources. Here, you can have this part of the screen and this part of video memory. Yes, you can talk to the sound card right now. Yes, you can have access to this USB device plugged into the computer, and so forth. But there are new challenges as well. If you think about it, you've got this guest operating system, and OSs have file system caching. They have ways that they interact with hardware devices to try to make the system fast. Well, now it's a guest in a host, and the host operating system and the guest operating system may have different ways that they want to manage caching. So this is something hypervisors need to take into account. Okay? So I don't think that's actually the this is the one that I was mentioning. So basically, the hypervisor has to find a way to keep the host from getting in the way of the guest operating system, in the way that it likes to solve problems. The other issue that I have here is that guest OSs expect to have access to hardware directly. So now the hypervisor has to find a way of providing this virtual interface that the guest OS expects to interact with. Okay? Just to touch on this issue, let's say that you're running an operating system and you want to change the page table of a process because the process's heap needs to grow. Okay? Some of you hopefully are remembering these details. Process's data segment needs to grow, so we change the memory mapping for the process, and now we start having page faults. A lot of this stuff actually involves touching protected mode registers. I'm only allowed to write to control register 3, which controls the memory mapping, if I'm the operating system, if I'm the kernel specifically. Well, what if the guest OS tries to touch that thing? Well, what happens is it generates a fault, and the hypervisor sets up something where it receives the fault, and then it can go ahead and it can either do what the guest OS wants to do, or you have some other interactions between these things. You also have the question, should the guest OS be able to tell that it's running inside of a hypervisor? Most of them can, okay? Because the OS is written in such a way, and the hypervisor is written in such a way that the guest can say, hey, am I in a hypervisor? And the hypervisor says, yes, you are, and they interact so that they can collaborate. So there's all these interesting interactions that start to show up when you start hosting operating systems. But it is the wave of the future. It's the wave of the present, really. Okay, other details we'll just go over really quickly. They are used in a lot of different contexts. The context clearly dictates what the OS needs to be good at. If I have a server system, I need to be really good at I/O. Maybe computation. I don't care about a GUI, so I don't need to do that kind of thing. Personal computers, well, I need to have a GUI, and it needs to be responsive, and so what if I waste some cycles being responsive that I could have used for computing? User interaction is most important, otherwise people are known to chuck computers across rooms and out of windows, so we need to try to avoid that. Let's see, you have mobile devices and tablets. New concerns. I'd like to be interactive, but I have limited energy, so I need to manage my battery life really carefully. Okay. And then, of course, I can install whatever application I want, so there's all kinds of interesting issues with that. And then connectivity may or may not remain, so I need to think about those issues as well. Let's see, what else? Embedded computers, you can read about that. We won't spend too much time talking about that. The last thing that I want to mention is real-time operating systems, because you hear this term a lot. Real-time operating systems means scheduling is really important. I have to have things done by a specific deadline. Most of the time when you see real-time support in operating systems, it is in a general purpose operating system, and the real-time support is soft real-time. We call it soft real-time because it's not a failure if the OS meets, or I should say, if the OS fails to meet the deadline. That's not a failure, okay? My kitten video gets stuttery, my music gets stuttery. I'm upset, but it's not the end of the world. The OS didn't crash. If you have a system where those scheduling deadlines must be met, and if they're not met, then it is considered a failure, then that is a hard real-time system. Okay? And it's an interesting exercise to think about what would be hard real-time OSs, but a really simple example is the automobile manufacturing assembly line. Because I've got the skeletons of these cars moving on conveyors, and then I've got these big robot arms which come in with their big welder and go bzz, bzz, and they make various welds. If I go and I try to make a weld and there's no car there, I have a problem. Or if the wrong part of the car is there, I have a problem. Those systems, it's a hard real-time requirement. And if I fail, then the entire assembly line needs to be shut down so that I can go and reset things, figure out what in the world caused this to go wrong. Okay? Any questions? All right, I think that's about all the overview that we have for today. So next time what we're going to do is start talking about the various facilities and OSs, and make sure you enroll in Moodle and make sure that you get your team survey to me ASAP so that I can go ahead and get that all sorted out. Okay, we'll go ahead and get started now then. This is another action-packed lecture, so we'll probably move at a brisk pace, but please feel free to ask questions if you have any along the way. There's also a lot of graphics, so the fact that it's a little bit long is probably balanced out by the lower content of each slide. So what we're going to spend some time talking about today is what generally is in an operating system. And again, this may seem like a really obvious thing, but it's actually really helpful to review it all because you have lines, and some things are on one side of the line and some things are on the other side of the line, and it's helpful to understand where things go and why. So we're going to spend a little bit of time talking about that today. Probably the most obvious things in this picture are the users and the computer hardware. I think we're all familiar with that. I just had to reboot my laptop. That's the hardware. I'm the user, and we intuitively understand what users want because we're all computer users. But they just want to solve some problems by using the computer hardware, give a lecture, solve a homework, surf the internet for pictures of chickens or whatever you happen to want to look up. So like it says here, the OS may have a variety of constraints on that front. It may have a single user constraint. It may actually most of the time have no users, or it may have many users most of the time. So you have different constraints that the operating system might need to operate within. An example would be the computer in your car. Most modern cars have a computer that helps them run more efficiently. It's extremely common now, and that computer basically only ever has a user when something's wrong with the car. And the mechanic has to go and plug a little thing in under your dashboard and get the error codes and see what's going on. So very simple user interface, 0 to 1 users. Most of the time it's 0. Hey, your cell phone is another example of a computer with typically only one user. You're doing stuff. Okay. So yeah, you have variations on what are required as far as the user interface is concerned. And also, if you think about it, what levels of multitasking are required, because if I only need a single user to be supported, then that makes it much easier to manage certain aspects of the system's data. So you can think about that in your own time. Applications are the things that the user uses, and the applications obviously depend on what the operating system provides to be able to implement what they need to do. But one thing that you may not be aware of is that a number of these applications are actually provided by the operating system itself. So we have this box labeled operating system, and really what that means is this is the part of the operating system that requires special access to the hardware. And then there's stuff that sits on top of the operating system proper, I'll say, that actually is still technically part of the operating system, but it's there to provide various services to applications. So like I say here, services for managing system resources, command shells, you'll get some experience with that this week, and graphical user interface programs. So I have an X server that can run on the system. It is definitely not part of the OS proper, and you'll understand what I mean by that by the end of the lecture. I'll clarify the meaning of that statement. And same thing with command shells. They typically run as user applications, and services like your internet firewall. If you're familiar with Linux system administration, then things like inetd, xinetd that manage networking, when somebody connects, what application is started, that kind of stuff. All of those things tend to be system applications that live outside of the operating system proper. Then there's user applications built on top of these things. And we're all familiar with these, like PowerPoint or Microsoft Word or Emacs, VI, those kinds of things, compilers, web servers. We've all used all of these kinds of tools to solve specific problems. And they interact both directly with the operating system when they need to do OS-specific things, and they also interact with system applications when they depend on various services that are offered outside of the OS, but still low enough level that they would benefit from it. Okay? Any questions so far? Like easy, right? Wow, who knew that operating systems were so simple? Then you have the OS itself, and it has a lot of different things that it might offer, but depending on the specific needs of the hardware or the context that it's being used in, you may not have all of these facilities offered. But this is going to be a very representative sample of what OSs generally offer. Now, the most obvious thing is program execution. Typically, unless you're working with an embedded system where you're always doing one thing and one thing alone. Like when I go upstairs to use the photocopier, now it's pretty advanced, but it has one job, make photocopies. And maybe it needs to enlarge or reduce or select different kinds of paper, but it's always running basically one program. But general purpose computers need the ability to run various programs. So we have to have an ability to do that. Like I say here, optionally you may have runtime linking, aka dynamic linking, that needs to occur. If you're not familiar with the differences between dynamic linking and static linking, it's not critical at this point. I don't think you really care about it in Pintos either. Yeah, so you're kind of lucky. Everything's statically linked, if I remember correctly, in Pintos. But this is so that you can have shared libraries and you can upgrade one library and fix all the applications that use it at once, those kinds of things. Program termination, either happy program termination or unhappy program termination. We may need to be able to signal between processes and so forth, although that's kind of covered by another facility. But if I receive a signal, I need to be able to terminate or respond to that signal and so forth. So this is all part of program execution. Another obvious facility is resource allocation. There's a lot of different kinds of resources on the computer. And if I say resource, you probably are thinking, okay, the memory heap is a good example of a resource. You know, I need to be able to have some DRAM that my program uses, and so that needs to be allocated. But another one, a really obvious one that you may not think of right away, is the CPU. Because I'm not the only program running on the computer. I may have 5 or 6 programs, or what is more likely the case is dozens and dozens of programs all running at the same time, and the operating system has to allocate the processor to the programs that are running that need the processor soonest, or they need it most. And if nobody needs it right away, there's nobody high priority, then it can give it to somebody who needs it less, but maybe needs it for longer. So you have various ways that the operating system can decide how to allocate the CPU. And then you have files, you have printers, you have all kinds of other things that might need to be managed by the operating system because different programs will want to access these resources. And the OS, like I said, is the government, and it decides who is going to get access to what and when. Okay? So that's the resources. Let me see. File systems, again, very common thing. We frequently have many different file systems that are supported by the operating system. I have a Mac. I've had a Mac for like 5 or 6 years, maybe a little bit longer now. And, it can support FAT32 because a lot of, memory cards, flash drives use FAT32 as a file system format. I mentioned the, ISO 9660 for optical drives. And then, of course, there's HPFS for the file system for the Mac. And then you can add other file systems as well. Mine happens to support NTFS for both reading and writing because I frequently plug Windows drives into my laptop and I need to be able to manipulate them. So you have various things like that. Okay. Now when you have file systems, then that means you have storage devices, and we talked a little bit about that last time, that there may be many different ways of interacting with them depending on the physical interface of the storage device into the hardware. So is it parallel ATA, serial ATA, SAS? Is it some network storage that I access through the network card and so forth? So you can see that we need some kind of I/O service that allows the operating system to interact with the computer hardware. We could just do this as, I need to interact with this device, so I'm going to write all the code and just have maybe a giant if statement, like what kind of device, then I'll have this code, or if it's this other device, then I'll have this code. Terrible architectural approach. But there are definitely operating systems that have chosen that approach and illustrated through experience that it's a terrible approach. What we definitely don't want, though, is applications to interact with hardware directly. I should say that probably 90% of the time we don't want applications interacting with hardware directly. There's definitely circumstances where we do, and we'll talk about some interesting ones in a couple lectures. There's a particular architectural approach to operating systems called exokernels, which is being explored more and more often, that allows direct access of applications to hardware. And it's really amazing what can be achieved, but it's also very constrained. But anyway, so we have some various details that need to be solved here. And so the typical approach is to have device drivers that are able to interact with specific kinds of devices. and then the device driver provides a unified, clean, simple interface to the operating system. And then that interaction occurs, and the device driver sort of encapsulates all the ugliness of interacting with hardware, okay? Which frequently can be very ugly. When we start talking about booting the Intel processor, and really I should say booting Intel personal computers, Intel-based personal computers, you have a lot of historical cruft that has accumulated over the years. And one of the funniest things is that, so you have 19 address lines on the oldest Intel processors. And then at some point they're like, oh, you know what would be really nice? A megabyte of memory. So why don't we go ahead and add more address lines? And so that 20th address line, they actually route it through the keyboard controller. Keyboard controller, what does that have to do with memory? But that's how they decided to set up the system. And so when you want to enable access to 1 megabyte or more of memory on, I should say Intel x86-based PCs, frequently what you do is you talk to the keyboard controller to turn on access to memory. And it's like, okay, this is really weird. And most systems ever since have done that because of the historical baggage there. We need to be able to support OSs that do it, and OSs need to support hardware that requires it. So it's just this horrible thing. Ugly. Anyway, so I/O services allow you to sort of encapsulate some of that and not have to deal with that all the time. Communication is an extremely important facility that operating systems generally have to provide. There's different kinds of communication. Again, if you think about it, there's a broad spectrum of communication technologies or facilities that need to be provided. And most of the time we think, oh, yeah, networking, because that's what we generally use all the time. But there's also interaction between processes that need to collaborate. We call it inter-process communication, or IPC, and it's actually extremely important, so important that there's a wide range of different ways that processes can interact with each other. I have a few of them listed. In fact, this is actually a pretty good, this is a pretty representative sample of them. So you have pipes between processes when they need to stream data to each other. You have shared memory if they want to share data structures. Postgres relies heavily on shared memory for its implementation to share data structures between various Postgres clients that are connected to the same database server. Message passing, not as commonly used, but it used to be really ubiquitous. Local sockets, so you actually have, again, you think sockets, you think networking, but you can actually on Unix open Unix sockets and again stream data between processes. It's extremely fast. It's one of the fastest ways you can pass data on a Unix system between processes. And then, of course, you have networking, and there's all kinds of networking technologies that we can support. Again, we think of internet networking or the internet protocol. You think of Wi-Fi. Okay, so that's something that sits under the IP protocol. You have Ethernet. You have what are more interesting are local networking technologies, Bluetooth, near-field communication becoming more common. I want to go put my phone on some other phone and they talk to each other and that kind of stuff. So you can do all of these things. So you can imagine that there's a lot of different facilities that might fall into that bucket. Accounting is also frequently very important. It's interesting because it's changed a lot over time. Remember that I said initially, historically, you would have one computer for a large organization. And you would even have situations where, well, this organization has a large computer. They don't use it all the time, so other organizations would come in and say, hey, can I use your computer when you're not using it? That's how rare and how expensive they were. And so you needed to do accounting for CPU time. Okay? We don't really do that anymore because processors are so cheap. It's easy to make them. It's easy to put them in anything. So we basically need some way of keeping track of resource usage that we can then use to factor into billing. Okay, so like I said, CPU time used to be extremely common. Now it's extremely uncommon, but now it's much more common to actually bill for storage and network use and so forth. Okay, bandwidth, those kinds of things. Yes?
Does something like AWS do this on their OS, or is that like...
That's a really good question. I can't speak to that directly. I used to work at a company where they were actually involved in content distribution networks, and a lot of times what you would do is just use the logs of various internet services that were already provided, or use existing OS facilities to record storage and network utilization, and then you could use that for billing. It was imprecise though, and if those services are inefficient, then that wastes CPU cycles that could be used. So I would not be surprised if companies tried to work those kinds of facilities into the operating system kernel to make it much faster, but and also more accurate, I would say. But I can't really speak specifically to AWS or other hosting providers. There's probably information about that on the internet, though. I would guess. Okay, let's see. Other things. Oh yes, error detection. Errors never happen. So we have to have some facility to figure out when errors occur and how to respond to them, and also how serious they are. So if I have a situation where my printer is out of paper, that is an error, and my computer will say, hey, I had a problem trying to print this document, or I couldn't connect to the printer, much less serious than a parity error in my memory or something like that, which probably, has anybody seen parity errors or any kind of memory failure errors? Wow, you guys are lucky. So live long enough and you probably will. So anyway, so you have various kinds of errors that can occur. Hard disk is full. I remember one time that I was working on NanoDB and I had a bug in the write-ahead logging, and it very rapidly created like a 45 gigabyte write-ahead log and filled up the rest of my disk. And I was like, oh man, now I have to delete this. And so I got onto the graphical interface, and I tried to drag that file into the trash, and that was like the wrong thing to do for the Mac, because it instantly, like, deer in headlights froze and fell over, and I'm like, oh man. So I rebooted it and then went in and deleted it at the command prompt because it couldn't handle that low a disk availability. So you have situations like that. How well does the OS respond to that kind of thing? File systems corrupt, various other things. You have less common errors that sometimes computers are able to respond to. Processor failure is a very interesting one. And the reason why it's interesting to me is that there is a company called Tandem which has made it their business to try to create processors that can detect when they fail and respond in some graceful way. And they have a specific processor called a non-stop processor, and it actually has two CPUs which execute the exact same sequence of instructions in lockstep. And what happens is, every time the instruction executes, it always compares the results. If the results ever don't match, then the processor says, don't trust me, and the system is able to reset back to a known good state and then resume execution and see if it can recover. Who needs that level of reliability? Well, stock exchanges, banks. You would want your bank to never lose information and to never have an inaccurate computation. A lot of people don't care, so we don't have that kind of facility in general, but in a few circumstances, it's necessary, and so people do that. Just as a little footnote, a bit of trivia, Tandem actually had a coffee mug that they had as a marketing, like some swag that you could hand out, and the coffee cup had two handles just to sort of illustrate, yeah, we have two cores in our processor. Okay, then you have various kinds of abuses that can occur. So, of course, you have to have some kind of security or protection facility. And you can imagine that malicious programs could be sitting outside of the computer. So you might have protection and security interacting with communication, like a firewall to protect the system. Or, of course, you have the potential for inside programs to be doing it as well. So applications are basically never allowed to interact directly with the operating system data structures or operating system code. And we'll talk about the requirement for computer hardware to provide some capabilities in this area in a second. But what happens is all interactions go through system calls. So that system call layer is the wall. It's the wall around the castle that protects the castle from being overthrown by some attacker. Okay? And so the system call interaction has to be rock solid, completely reliable, and when you get into the system call project, you'll see this is how they work, and we'll talk about various techniques for making sure that that section is actually really reliable. When you have things like, you've probably heard of privilege escalation exploits, things like that, or even things that cause kernel oopses and really infrequent errors like that. A lot of times it's because there's bugs in the system call API that can be exploited by programs, and that's no big shock because, hey, system calls are implemented by programmers, and programmers are known to create bugs, so it happens. Okay, yeah, so operating system has to protect processes from each other. So processes should only be allowed to interact when they both specifically agree to interact. I should only be able to allow a pipe between processes or two processes to share memory when both processes specifically agree to do so. And that is generally the rule that's followed by virtually all operating systems that don't suck. And of course, there's specific support required by the computer, or required from the computer hardware to implement this kind of facility. We will spend a lot of time talking about computer hardware in the future, but in fact, there'll be times where your eyes will probably glaze over unless you're a double E and just get totally excited about this kind of thing. Because unfortunately, software has to run on hardware. I know that computer scientists are sad about it, and probably electrical engineers are sad about it too. But that's just the unfortunate reality. And there's a lot of little crufty stuff that you have to deal with. And so again, you may have some weird hoop that you have to jump through to get some peripheral to talk to you correctly. And anybody who's done any sort of embedded system work knows that. I mean, I took 5X. I remember a lot of little things like that and those were just simple systems compared to some of them out there. Okay, so the two features that we really need to have on our computer hardware, we're going to talk about only two right now. One is having multiple operating modes so that the processor itself physically enforces the difference between programs operating in the operating system and programs operating outside of the operating system. We need some way of enforcing a distinction there. The most limited requirement that we must have is some ability to have kernel mode versus user mode. Okay? And kernel mode has a lot of different names. I'm sure you've heard that term a lot. Protected mode, privileged mode, and so forth. And in kernel mode, you can basically do everything the processor can do. Okay? That's what kernel mode basically means. I can do anything. And user mode means I have a restricted set of facilities that I'm allowed to use. And it's also known as normal mode. Okay, but frequently it's called user mode. So what is a kernel? Well, the simple answer is the kernel is whatever software runs in kernel mode. I don't know if you were expecting a more beautiful, like elegant, theoretical answer than that, but the kernel is just a part of the operating system that runs in kernel mode. Okay? It is that simple. And there may be many other components running in user mode. And this is one of the interesting questions that arises when you start looking at computer operating system architecture is, well, what parts should be in kernel mode? Because the kernel can do anything. So it's like, well, the more code in there, the more likely we'll have bugs. So that could be bad. But the more code I have in there, maybe the faster it'll be. And if I move stuff into user mode, then that'll be safer. But then the transition, remember, from user mode to kernel mode is slow. Certainly slower than just executing in kernel mode. And so there's performance impacts. And so we'll talk about a number of those things in the next two lectures. There are processors that provide more than two operating modes. This is one of the pictures from CS124. IA32 has 4 protection levels. They're called hierarchical protection domains because they are nested. So level 0 can do everything that level 0 is allowed to do, obviously, and also level 1 and level 2 and level 3. Level 1 is allowed to do everything but the level 0 stuff, and so forth. Okay? And so typically, like Linux is really simple because Linux has to run on a whole bunch of different computer systems. Linux will use ring 0 and ring 3. And that's basically all it'll do. A lot of hypervisors for actually hosting operating systems on other operating systems will run guest operating systems at level 1. So the host operating system stays at level 0, the guest is at level 1, and then applications are at level 3. Okay, so you have various ways in which these things are done. Okay, talked about that. But there's even more operating modes on different kinds of processors. Most cell phones run some variant of an ARM processor. It's a RISC processor. And, so you think, okay, these are mobile phone processors, and they are limited in some ways. But look at how many different protection levels they can have. 8. Why might they have 8 different protection levels? Well, it's kind of interesting. If you read the ARM specification, which I don't know if some of you may have, but like if I'm making a phone call, probably the software should be allowed to do different things than when I'm not making a phone call, or I'm in the sleep mode, or I'm off, or things like that. So the different protection levels basically allow you to constrain what applications are allowed to do or what software is allowed to do in these various states that the device can be in. And so that's what gives rise to so many different protection levels on the processor. Okay, just some details there. Let's see, second feature that must be provided is virtual memory. And again, you may recognize this picture from CS124, but we need to have some way of giving processes a virtual address space that we then, as the operating system, get to control the mapping to physical address space. Okay? And so you have this component on the processor called the Memory Management Unit, MMU, and it takes addresses from programs and translates them in hardware into physical addresses that go to memory. And there is some mapping. Typically, we use page tables to define the mapping from virtual addresses to physical addresses. So the page table and the MMU are both managed by the operating system. Applications cannot be allowed to do that. Otherwise, I could just go and edit my page table and say, hey, I'd like to see the other process over there and see what they're doing, and it would be fine. The processor would just do it. So MMU configuration and control is a kernel mode operation, and the page table typically is in protected regions of memory that only the kernel can access. Okay. Makes total sense, right? Let me see if I see anything else on this slide. Yeah, so we'll discuss virtual memory a lot more in the future. This is not the only way to do virtual memory. There's some really interesting older ways that were used to do virtual memory, which are now kind of not very exciting anymore. And I think that they really haven't scaled very well to current memory sizes, which is why they've kind of fallen by the wayside. But we will spend a little bit of time talking about them because there's some really interesting little nuances and details about virtual memory if you go back and look at some of the historical stuff. Okay. So this is what we're able to do with this. We create an address space, and this happens to be a 32-bit application address space. I don't know if you've gotten to the point where you recognize this. I certainly have, but I teach these classes every year, so it kind of sinks into your head. But we have a 4 gigabyte address space that we can access, and basically the operating system can define each process's address space separately. Now that said, we always follow a single pattern because why come up with some weird situation where every process has some really wildly different address layout? That would be crazy. And so you always have certain boundaries that are fixed. Like in 32-bit Linux, you always have the top gigabyte allocated to the kernel and the bottom 3 gigabytes allocated to the user process. Okay? Just the place where they drew the line. Okay? The stack is always at the top and grows down, and you see interesting little variations where on Linux they will start the stack at different places, so function stack frames don't always end up at the exact same address. It makes it much more difficult to create exploits for the system. Okay? And you have various other things that can be changed, varied as well, like the shared library utilization may vary depending on the way the program executes, because libraries may not be needed until some point, and then when they're loaded, they may end up at different locations than they started, than they might have been at the previous execution, and so forth. Okay? This whole layout, by the way, we call it an application binary interface. The operating system has to specify how applications are laid out so the OS can interact with the application can be started properly, and the application can terminate properly. So things like this are, again, part of the specification of the operating system. There's no one right way to do it. There's some better ideas and some worse ideas, but this is the general approach. You have to have some pattern that the operating system always follows. Now you also notice some of these little details here. At the very top I have, the part that I said is kernel stuff. That part is actually constrained by the kernel through the page table structure, that this memory region is only accessible from kernel mode code. So if user mode code tries to access this stuff, you get a protection fault. And then the kernel steps in and says, what are you trying to do? And the application probably dies. Okay, that tends to be what happens. So, but you have various details. You have process-specific data, which we'll talk about some examples of that. And then you also have stuff that's global, like kernel code. All processes need to be able to see the same kernel code so that the kernel can do its thing. And if you think about it, when I switch from one process to another process in a context switch, I'm changing the virtual address mapping, but that happens in the kernel code. So when I apply that change, I need there to still be kernel code in the new process's virtual memory. So I have to make sure that mapping stays the same so that when I switch over, I don't suddenly find myself in La La Land, and now I have a problem. So there's things like this that the kernel has to think about in its memory layout. Okay, and there's various details. I'm going to talk about some of those things, well, obviously in future lectures, and we'll have a few examples of that here. But the process is not allowed to manage these details directly. The kernel manages it on behalf of the process, even though it is specific to the process. Okay, I should probably pause and ask, has anybody got any questions or anything like that? Okay, because I know I've just kind of been rattling through. So please feel free to speak up if you have any questions. Now the example we're going to look at, and it's very relevant to creating an operating system shell, especially because you're all Caltech students and I'm going to make you do harder things than normally people have to do. Because they're not that much harder, and if you know how to do them, you can impress people and be a badass. So that's why we're going to raise the bar a little bit. But we're going to talk about console I/O and file I/O. Okay? You start a program on the computer. You go in and you click Chrome, or you start the command prompt and try to do your CS11 assignment or something like that. When you start that program, there's certain facilities that the operating system always sets up for that program. Some of them are obvious. I need a stack. I need a memory heap. Okay? But there's other ones as well, like standard input and standard output and standard error. Okay? Those things need to be set up. I printf, where does it go? Well, the OS sets that up for me. I scanf, where does that go? Well, it also, whatever the OS sets up, that's where it comes from, I should say. So, if you look at this, standard input and output and error streams can actually come from or go to a variety of locations. We're used to them being the console. I'm used to typing into my programs. I'm used to seeing output on the console when my program outputs things. So that's a pretty obvious one. But what are some other places that data can come from when I run a program on the console? Anybody got some like mad sysadmin skills that's done like pipe commands and things like that? Yeah, exactly. You can have one command that runs, and its output, you're saying, well, this is useful output for the second program, so you pipe it into the next one. And then it does something, and you pipe it to the next one. Well, what's another option? So you have programs can give data to programs. What else? There's another pretty obvious one. When I say it, you'll be like, oh, okay, yeah, of course. Yeah. Yeah, you can redirect output of a program to a file. Similarly, yeah.
Dev null, dev random.
Yeah. So you have special devices that you can also pipe output to if you don't care. I've done that from time to time, just send the output to dev null, because it turns out that when you have a program running and it's printing to the console, just the effort of printing it to the console slows down the program. I've got a lot of user interface to update. I've got I/O I'm performing. So if I send it all to dev null, I'll get a much more accurate measure of just the computational effort of the program. So pretty common. And from dev random, dev zero, there's a couple of other special devices, which we'll probably talk about more when we get to shared memory. Okay. Yeah, so, and another thing, of course, is you can pipe an input file into a program to tell the program, it's like, yeah, I'm a user, but just take the input from this file instead. And so that's another thing that you can do. Okay, so redirected to and from disk files, so the program sees on its standard input some files contents. When it writes, it goes to some other file, or to and from another process. Okay? So these are all very common mechanisms, and you'll get a lot of practice with this term, I believe. I hope you do. If you don't, then I'm going to be really sad. But these are the kinds of things that are pretty ubiquitous when it comes to using computer systems, administrating computer systems. I don't know if I make it through a day without doing some kind of piped operation at the command prompt, unless I just don't touch the computer that whole day. So it's pretty common. Now, all input and output are done with Unix system calls. Okay? So you have read and write, and this is what read and write look like. You may get to work with these on assignment 1. I will give you some applications to use for testing that use these functions, and so you can see how they're utilized in a very simple Unix application. It's really straightforward. But you'll notice that they either attempt to read or write some number of bytes specified by n byte, so n byte being number of bytes. It's a size t, which is an unsigned integer or an unsigned long, but I'm presuming that most of the time it's an unsigned integer. And then the value returned is an s size t. Does anybody know the difference between size t and s size t? The S stands for signed. Because basically, the function will return 0 for EOF. It will return a greater than 0 value to say I read or wrote some bytes. And it will return a negative value to indicate an error. So it has to be a signed size. Don't even ask me what happens if I pass a value that's, that can be represented in size t and can't be represented in signed size t. Scary design problem. Okay, that's an API issue that needs to be dealt with. Okay, so what these functions do is they do not read or write data to the file. They request that the kernel reads or writes data from the file, or standard in or standard out or the socket or whatever. Okay, so these are system calls, and they frequently take a long time. And so if you remember from CS124, that's a great opportunity to do a context switch. So we'll just flip over to somebody else and get some real work done while we wait for read or write to finish. Wait for the user to take like 15 seconds to decide what they want to write to the instant message they just received or whatever. Oh, yeah, let me point out some things. You see file des, buff, and n byte. Now, n byte is pretty obvious. Number of bytes. Buffer, also pretty obvious. We call it a void star because we just want to access individual bytes. We don't care about the type of the values that we're reading or writing into. We're just reading and writing bytes. Okay? But file des is the thing I want to talk about next. So you have the file descriptor, and it's just some non-negative integer. So it could be 0, but it could be 6, it could be 19, it could be something like that. It cannot be negative, and you'll see why in a moment. Processes can have multiple open files, and so this is a kernel data structure managed for the process. I have an array of pointers, and each entry in this array of pointers points to an open file, or it will be set to null if it's a closed file. It's not being used. And so we have these file structs. Okay. Now I should mention at this point that this is a representative example of how this is implemented. Different operating systems will have different ways of doing these things. Linux has a different set of data structures, which if you look at the inside the Linux kernel book, then it'll explain the data structures for Linux. But this is a representative example of how it's done. And you can see you have things like, well, what mode flags do I have? Should I truncate when I open? Or should I always seek to the end before doing writes? Or what kinds of things should I do? You have a file offset. Where should the next read or write occur? And I have this weird v pointer thing. So file des is just the index into this array. That's all it is. So file descriptor 0 is for the first file that the process has opened. That's in file 0. Okay? And so you can see that there's a, like you can say ulimit and set the maximum number of open files. All you're really doing is for that process, setting the size of that array. That's all it does. Okay? It's not dynamically resizable, at least not in the way Unix is implemented. One could create an operating system in which that were the case, but that's not how Unix is defined. Okay. All right, so yeah, and processes are simply not allowed to directly manipulate this. I already kind of belabored that, so I'm not going to spend any more time on it. Are there any questions so far? Because it gets more complicated. You're like, oh yeah, this operating stuff is really simple. Okay, now these file structs reference the actual file that's open. Because so far we don't have enough information to know where is it on the disk. You know, like this inode thing that says, well, where is the actual chunk of data that I'm looking at on the disk, or the directory entry for it, or things like that will be recorded in that data structure. So you can see that the file struct references the details of how to interact with the file. Okay. And this file ops is the really interesting part of it. Because that file ops pointer points to a collection of function pointers that can be used for performing the common operations. So file operations will have a function pointer for reading, and it'll have a function pointer for writing, and it'll have a function pointer for closing. It'll have a function pointer for seeking. All of these kinds of common operations that I want to be able to do on any file descriptor. And when you look at the API, you saw it in the first, we didn't talk about it very much. I just listed the functions. But when you actually dig into it for the first assignment and start seeing file descriptor, file descriptor, file descriptor, they all have this structure, and a file descriptor could be a socket. It could be a UNIX socket, so it's not even a network socket, it's a UNIX socket. It could be a file, it could be the console, it could be any number of other things. It could be a pipe between processes. So how do I provide the same API for all these things? By using function pointers. They're your friend in operating systems, like a lot. Okay, so file ops has these things. And notice it takes basically similar arguments, but slightly different, because now we actually get the file star that contains the data for the actual thing we're interacting with, not just a file descriptor. So we're able to map that, and then the buffer and the number of bytes are mapped right through. Okay, does that make sense? Yay, indirection is like favorite thing in the world. Okay, so the kernel can implement the read system call and the write system call very easily. It just goes and says, hey, is this file open? If not, return the appropriate error message, blah, blah, blah. You can go ahead and look at all of that yourself. But if it's open, then it can just pull the file object and then use a similar line of code to this. Say, okay, I want to follow vpointer, I want to follow file ops, and then I want to do the read operation. And here's the file object. Notice the file star goes in because I have to know what offset. I have to know these details to be able to know what does the process actually need to do. Okay, what are the flags I should be enforcing on this file for this process? Okay, make sense? Pretty neat, right? I mean, this is all like basic C code. Maybe the only thing that's scary is the function pointer thing. But seriously, once you get comfortable with function pointers, it's like, oh, that's so simple. Okay. Pretty nifty stuff. I love it. Okay, so this also is how we allow multiple processes to have the same file open, maybe reading and writing at different offsets. Like I said, Postgres. Let me just give you a little bit of background about how Postgres works. Postgres is a database server, one of my favorites. I spent like a year and a half working in the code base of Postgres, so I really love, it's a really neat database. It does a lot of cool stuff. And Postgres, every time a client connects, starts another process. So they're not threads in a single process, they're separate processes. And the whole point is that if one of the processes like explodes, then it doesn't take out all the other Postgres processes and so forth. It's a very stable approach to creating a database server. And so they all manipulate the same data files in the same shared memory areas, and so they need to be able to share files like this. Okay, so each process has its own read-write offset. You notice the file struct has the offset in it and the flags, but they all point to a single shared thing that represents the file itself on the disk or whatever. Okay, so this is how this stuff works. Now, when a Unix process is started, it has to set up input, output, and error streams. They're set up automatically. And what you'll notice is that virtually every operating system follows this rule that file descriptor 0 is standard input, file descriptor 1 is standard output, file descriptor 2 is standard error. And I say almost always. It is so almost always that there's a ton of code out there written that just hard codes file descriptor 0, hard codes file descriptor 1, hard codes file descriptor 2. Like, it's so almost always that if anybody tried to change it, tons of the internet would break. That's how almost always it is. Okay? Nonetheless, you still have to be a good programmer. And so you need to use special definitions for this thing. It's kind of like null is almost always 0, but I don't think anything says it has to be 0. And so you'd like to use null and not hard code 0 into your programs. Okay, C++ finally fixed their issues with that in C++ 11. But anyway, so you want to use standard in file no, standard out file no, and standard error file no. Okay? Those are the file descriptors. And yes, they're defined to be 0, 1, and 2. Now, programs basically don't care where data comes from or where data goes to. That is not 100% the case, because sometimes you have programs that behave differently if they're reading from files versus if they're reading from the console. And there's Unix APIs that basically allow you to say, is this a TTY, teletype interface or something like that, or is it a block device, is it a file, can I interact with it in different ways? So you do have a way of telling, but most programs don't care. Probably most of you have never written a program that cares about where its input comes from or where its output goes to. But command shells care a lot, because they have to take crap like this and figure out what to do with it. Okay? So you type something like this. This is the kind of thing that I would type a lot for one of my, actually this is one small part of a long sequence of commands I would type for a little thing where I was trying to figure out what some little gateway was allowing through and what things it was preventing to go through. So I would have to look at stuff like this. Logfile.txt would show up on grep's standard input, and the results would go into output.txt. So the shell, when it's setting this command up, has to say, okay, grep needs standard in to actually be this file. So it goes in and sets the file descriptor for standard input to be this file, not the console. Okay? And same thing for output.txt. It sets up the standard output to be output.txt, not the console. Okay? And of course, like I say here, if output.txt exists, it's truncated. Again, that's just a decision that is made that all Unix shells basically follow. You do a single greater than to truncate the file, or you can do a double greater than, and it will append instead of truncating. And then, like I say here, once standard input and standard output are set up, then grep is invoked. And what grep receives is not less than logfile.txt greater than output.txt, because that's consumed by the command shell. What grep gets is two arguments, grep and allow. And you'll see that argv always has one more element than argc has. Okay, this is, again, a specified behavior of Unix operating systems, that argv will always be terminated with null, so that you can just run through the arguments, and when you see a null argument, you can stop looking. Okay, that's how argv works. So argc is 2, and argv is going to have 3 elements, grep, allow, and null. Okay, any questions about this? You have to implement behavior like this, so good time to ask. Okay, so command shells basically follow this process, and I think that we're all generally familiar with it, so I'll run through it. Wait for a command to be entered, tokenize the command. If the first token is an internal command, handle it. So that tends to be done separately inside the command shell, then go back to the first statement. Otherwise, fork, and then wait for that child process to terminate, because the command shell shouldn't show a prompt in the middle of whatever the program is doing. That would be confusing. The child process, of course, looks to see if there's any redirection, because it has the same data the parent had, because it's a clone. And it modifies standard input, standard output, and standard error if necessary, removes those tokens, and then calls execve to run the program. Okay? And there's a few other ones as well. There's execp if you want to search the path, and there's a few other execs. I think I point you to some of them in the documentation for the assignment. Okay, but this is the basic idea. Of course, if execve, or it's one of its family members, returns, then you're sad, because the program couldn't be started. File not found, too many processes, out of memory, no permission, whatever. So there's a variety of ways that it can fail. So you need to report that error, and then the parent sees the child terminated, and it goes on to wait for another command. Okay, that makes sense? Pretty easy. So how does a child output get the command shell's output? So this is pretty straightforward. Just remember that Unix processes, when they fork, are virtually identical except for the process ID and the parent process ID. Those are the only two things that are different. And so the child gets all the same files open as the parent has, and they have the exact same file descriptors. Should be pretty obvious now that you understand a little bit more of what goes on under the hood. Okay, so you have this command shell and the child process is started. All of these things are duplicated, and you can see that the file structs are duplicated. They all point to the same kernel global open files. So it's very straightforward. The same standard input, standard output, and standard error. Okay, now if a command redirects, It's a bad idea to do it before forking because now you're going to mess up the command shell's state when you only want to modify the child process's state. So what you need to do is have the child process do the redirection, and then the command shell can just keep having standard input and standard output. Okay, that tends to be the way these things are done. Okay? All right, yeah, and so yeah, like I say here, the child process sets up standard input, standard output, and standard error before executing. Okay, so the next question. How does the process change the file descriptor stuff? Because remember, this is all in the kernel. I can't go and manipulate it directly. So the operating system provides a couple of different system calls. You have dupe and dupe2. And these are for duplicating file descriptors. Dupe just makes a copy of one using the, it creates a new previously unused file descriptor, but it's the lowest value one possible. So it'll fill in spaces if there's spaces available. So you hear you call dupe, then it'll go ahead and have another thing pointing to the same thing. Now, there's an interesting detail. I'll try to run through this fast. That when file descriptors are duplicated, the file structure is not. And so these two file descriptors actually have the same offset, which is a little bit weird. So you read from one, and then you read from the next file descriptor that both point to the same file. You're going to just keep advancing a single offset, which is kind of interesting. Okay, and you do need to call close on each one because that file object will not be reclaimed until its reference count hits 0. So you need to make sure that that gets mopped up. Then you have dupe2, which is a more interesting one, which basically allows you to say, this is the file descriptor I want you to duplicate into. Like it says here, if the second one is already an open file, then it is closed before the new file descriptor, I should say before the old file descriptor is duplicated into the new one. Okay. So this is how you can actually replace standard input or standard output on a process. You say dupe2, the file I want to use for standard output, or I should say, yeah, where standard output should go, put that where standard output normally lives. And now when the program runs, it'll just write into the file. And then you have to close FD because now standard out file no will point to it. Any questions? Yes?
So would the parent process give you FD and then the child process would replace standard out with FD?
You have a number of choices on how you implement that. The general approach that people follow is the parent process gives the child process the file name. The child process tries to open the file, and if it fails, it can print an error. Otherwise, it'll have the file descriptor and can duplicate that into standard out before execing. Yeah. Any other questions? Okay, just last thing to show you this example. So the command shell forks. You have input file descriptor and output file descriptor. You open the input file. You duplicate it into standard in. You close the input file descriptor because now standard in refers to it. Output file, you open it with create, truncate, write only. You truncate because remember, single greater than always truncates. You would just set it to append if you wanted to do double greater than. Dupe2 that into standard out, close the original file descriptor, and then exec, and off it goes. Okay? Pretty neat. Okay, so next time we'll start talking about operating system architecture. We have 2 lectures on that, and then an overview of the computer hardware and interface with the operating system. So see you all next time.